Hey everybody, this is Dr. Ban. I wanted to go over a couple of problems that were in the homework from chapter 13 and just to make sure that everybody's on the same page in terms of how to do these problems. So the first one is problem 1358, which is the problem is cyclopropane C3H6 is a gas used as a general anesthetic and undergoes a slow molecular rearrangement to propylene. So you have cyclopropane goes to propylene. And then at a certain temperature, the following data were obtained. And they have initial concentrations versus the rate of formation. And there are two questions. One is, what is the rate law for the reaction? And then, what is the rate constant? And so how do you set up this problem? Well, the first thing that you want to do is you want to write down the rate law. And you don't know what the exponents are going to be in the rate law, but you go ahead and write down the rate law. So that would be rate equals the rate constant times the concentration of cyclopropane. Okay? And in order to determine the exponent here, you need to figure out how the rate changes as a function of the concentration of cyclopropane. Okay, and you can take 2 points and just see how the rate changes. So, and you can take any 2 points. So I'm just going to pick the difference between 0.1 and 0.05 concentrations. So, and I'm going to start off with 5.9 times 10 to the minus 5th. So I'm going to write 5.9 times 10 to the minus 5th molar per second equals the rate constant times the concentration of cyclopropane, which is 0.1. And then I'm going to divide that by another time point, in this case 0.05, which has a rate of formation of propylene of 2.95 times 10 to the minus 5th molar per second. So that's 2.95 times 10 to the minus 5th molar per second equals K times 0.05. Okay, so the K's are going to cancel out. 0.1 divided by 0.05 is 2. And then let's just clear this. So is it 5.9 or 5.95? I can't remember. 5.9. So 5.9 be 5 negative, divide that by 2.95 negative 5 times 10 to the minus 5th is 2. So 2 to the what power gives you 2? Well, that's 2 to the 1. So the exponent here must be 1. So the rate law for this reaction is rate is equal to K times cyclopropane to the 1 power. Okay? And then if I wanted to calculate the rate constant, I could just solve for K for any concentration of cyclopropane. So I could take 5.9 times 10 to the minus 5th divided by 0.1. Okay. So if I say K would be 5.9 times 10 to the minus 5th molar per second divided by 0.1 molar. So K, the molars are going to cancel out. K is going to be 5.9, 5 negative, divide that by 0.1 equals 0.00059. So 5.9 times 10 to the minus 1, 2, 3, 4 times 10 to the minus 4 per second. How about this other one here? We could double check it by plugging in another set of values. So we could have 2.95. It's 10 to the minus 5th per second. Divide that by 0.05. Oops. K in this case would be, this is molar. Molars cancel out again. And 2.95. Divide that by 0.05. Again, we get 1, 2, 3, 4, 5.9 times 10 to the minus 4. 10 to the minus 4 per second. So whoops. Sorry about that. Okay, so the rate 5.9 times 10 to the minus, the rate constant is 5.9 times 10 to the minus 4th reciprocal seconds. Okay. So that's the first one. The second one is going to be a little bit more complicated. Okay, but it basically is going to ask you to do the same thing. This one I'm not going to go through the gory details. I think you can see the answer to this problem just by looking at it. Okay. So the following data were obtained for the reaction of CH3,3-CBr with hydroxide ion at 55 degrees Celsius. They give us the initial concentrations of CH3,3-CBr, initial concentration of OH minus, and then the rates. So let's just look at this and see. Okay, so the first thing you would do is you would say, well, I want, let's say that I wanted to determine the order with respect to the OH minus concentration. Well, I guess first of all, what we need to do is to write down the rate law for this. Okay, the rate law is going to be the rate will equal the rate constant times the concentration of this times the concentration of that. So that's going to be rate equals K times the concentration of CH3,3-CBr times the concentration of OH minus. Okay, we don't know what the exponents are yet, but we can figure this out just by visually looking at the data. So let's say that I hold the hydroxide ion concentration. I want to look for the exponent in the OH minus, the hydroxide ion concentration. So I'm going to be varying the concentration of hydroxide ion while keeping the concentration of CH3CBr constant. Okay, that's going to allow me to get the exponent for the OH minus. So let's see. So we've got 3 places where the CH3CBr concentration is constant. Okay, and we vary the hydroxide ion concentration. So that's this one here, this one, and this one. And so the CH3CBr concentrations are constant. What happens, in the case of the hydroxide ion concentration, we go from 0.1 to 0.2 to 0.3. So a 3-fold change in the hydroxide ion concentration. And what happens to the rate? Well, we see that this one is 1 times 10 to the minus 3. If we double the concentration of hydroxide ion, the rate is still 1 times 10 to the minus 3. If we triple the rate of the hydroxide, triple the concentration of the hydroxide ion, we still get a rate of 1 times 10 to the minus 3. So what that tells us is that the rate is independent of the hydroxide ion concentration. So the rate, the exponent for the OH minus, we already know is going to be 0. Okay? Okay. And for determining the exponent in the CH3CBr, we have to keep the hydroxide ion concentration constant, and we vary the CH3CBr concentration. So that's the first 3 over here. So if we start off at 0.1, the rate is 1 times 10 to the minus 3. If we go to 0.2, which is a 2-fold increase in the concentration, we see we get a 2-fold increase in the rate. If we have a 3-fold increase in the concentration, we get a 3-fold increase in the rate. And we could take, say this rate expression here and divide it by this rate expression here. So you would have 3 times 10 to the minus 3 molar per second equals K times this is 0.3 times 0.1. This is 1 times 10 to the minus 3 per second equals K times 0.1 times 0.1. Okay, 0.1, 1 times 10 to the minus 3. And we see the rate constants cancel out. This cancels out. 0.3 divided by 0.1 is 3. 3 times 10 to the minus 3 divided by 1 times 10 to the minus 3 is 3. So what exponent do I need to raise this to in order to give me this value? So that would be 1. So the CH3CBr exponent here is going to be 1. And you could have 2 different rate laws in this case. You could have rate is equal to this, or you could just leave out the hydroxide ion concentration altogether, and that would give you CH3 3CBr. Okay, and then as before, if I want to find out what the rate constant is, I could just plug in any of these values into this rate law to give me my rate constant. And that's how you would go about solving those 2 problems. So I think I'm going to stop for now. And anyway, hope that helped.